Okay, so we have a next talk on to annotate or not, predicting performance drop under domain shift.
Thank you. Hello everybody, I'm Heidi from Naval Labs, and today I'll be presenting a work in collaboration with Matthias Galli. We both work in Naval Labs Europe, and it's about predicting performance drop under domain shift. So the motivation of our talk today is about lowering the maintenance cost of machine learning models in production. The assumption we always have that when we train our machine learning model, we have this spaghetti monster that generates your data, and at production time you assume your data comes from the same spaghetti monster. And since you train on the same distribution of data, then at production time you get excellent results. But in reality, there is a domain shift that happens where you get a slightly different version of the same spaghetti monster that gives you different examples. And then sometimes it goes nice, sometimes it doesn't. So how could we predict this performance drop, right? More realistically, you wouldn't get one type of domain shifts. You would get a set of spaghetti monsters that mix together and generate you this mix of data sets, mix of examples that is hard to deal with, right? But you still have to deal with it. So the way that people have been maintaining machine learning models in production is basically they sample from the data in production, and then they will annotate manually some evaluation data sets, and then they will evaluate their models on those evaluation data sets. And then they will detect the performance, and the performance is going nice, then they will keep doing this forever. This maintenance loop is quite costly. It costs a lot of time and money. It's prohibitively slow, so we cannot actually use it as triggers. So if something goes wrong as domain shift, we cannot do this in production time, and then it goes forever. So we don't see a way when this loop will stop at one time. So the goal of our talk today is to find a way to estimate this performance drop without needing any new without labeling any new examples from the target side. So imagine you have this fortune cookie that will tell you, you will open it every day in the morning, and then it will tell you, oh, your model today will have 12% drop in performance. How we do that? So imagine you will have a domain shift. This domain shift, you can use some sort, and as we will explain later, some sort of domain shift detection metrics to measure a value of this domain shift, and then we will find another way to move from this value to the actual drop in performance, right? So, domain shift detection metrics. There have been a lot of several separate families of or lines of work that talks about domain shift detection metrics. We surveyed lots of work and we grouped them into 3 types of families. The first one is about edge diversions, and the recent manifestations of it is the domain adaptation neural networks, or domain GANs. And then you will have the confidence estimation for out of distribution detection, and these are the families that's related to the confidence calibration of modern neural network and so on and so forth. And then we have the last one, which is the reverse classification accuracies, and it has nice formalism that's actually associated to cross-validation techniques. We're not going to go through all of them in details, but to give you a flavor of how this works. So there is the A distance is actually has nice formalism, but it's hard to compute in practice, or hard to compute exactly. So it's approximated to a classifier, for example, that classifies between inputs from source domain and target domain. And the intuition here, if that classifier does a good job, then the domain shift between both is quite different, right? And this is called proxy A distance. And we will keep this example of proxy A distance across the presentation. But in the paper, we selected 3 types of metrics. The first one we call PAD, and the other one we call CONF, which is abbreviation of confidence, difference in confidence scores. And the last one is called reverse classification accuracy. If you'd like to know more in details about these measures, I would advise you to look in the paper. The only thing here is that we have to know that those actually are unsupervised, so most of them you can measure domain shift without labels from the target domain. So that's important to keep in mind. So the question is, okay, we have those metrics, can we use them to measure the performance drop? So to know this, we actually devised some experiments where we calculate those, we simulate the domain shift by collecting data sets from different domains. And then what we do, we calculate this, these three measures that we detected, that we chose, and the corresponding accuracy drop. And now from these graphs or from these scatter plots, we can find that, well, there's some sort of global correlation. Sometimes it's noisy, but it might lead us to something, right? So that's positive already, that's okay. So we found one challenge is actually some of those domain shift detection metrics are task irrelevant. So meaning that large detected domain shifts might be actually inflected in, maybe they don't inflect large performance drop. So we exploit this using some adversarial domain shifts. So we add some, so think of them as adversarial attacks that add some extreme amount of domain shifts, but they are task irrelevant. So if we look at the pad, the metrics I explained earlier, you can find that the same correlation or the same scatter plot goes into actually 1 all the time, regardless of what accuracy drop you have. And that's basically because we added some set of adversarial domain shifts that's task irrelevant. So your model in production doesn't really, or your trained classifier wouldn't really care about those tokens in practice. And we can think of these as false alarms. So if you use those domain shift detection metrics at test time, you will get like alarms all the time that actually don't correspond to drop in performance. So the way we thought to do is basically how to adapt those models to make them task relevant. And we propose a modification of the pad into a pad star that actually brings back this linear correlation, right? So accordingly, we added a modifications, or we did a task calibration of all the proposed 3 domain shift domain detection metrics to be task dependent, right? So it seems fine now. We retain this correlation. It's task relevant. So can we still use it for actually estimating the performance drop? Then still, how if I get a value of 0.2 over pad, how this corresponds to actual drop in performance? So this is still unclear here, right? If we look actually in this into this global correlation, we can find that this correlation, yeah, there is a global correlation between inputs and outputs, but if you look closely, we can find that this is actually model specific. So the values of those metrics are actually depending on the model. And by model here, I don't mean architecture, I mean also how it's trained, the architecture and the seed in it. So you can find actually that when we train on the DVD domain using Elmo and bi-LSTMs and the seed of certain thing, we can find that when there is a huge drop, the pad metric gives you this amount. But when you train on books and bi-LSTMs and using random initialization, you get lower values of performance drop. And this kind of makes sense because if you have a classifier that overfits, it will have huge performance drop than a classifier who is well regularized. So following this intuition, we propose a method to go from the pad or those domain shift detection metrics into actually a drop in performance. So given a source domain that we have, and we have training data sets from it, and a target domain where we have, where we don't have labels, and this is your model, you will assume is a set of available data sets, evaluation data sets, and these can be sampled with bias from your training data set, or can be other evaluation data sets available in academia, for example. And then you would train your model, and then use every of these evaluation data sets. So you will calculate you can calculate the domain shift detection metrics on these because we only need the input, but we can also calculate the accuracy drop between the training time and the test time, training domain and the test domain, because we have those labels for the test data set. And then we plot a graph between the domain shift detection metric and the accuracy drop that is really depending on your model, right? And then we do regression, a regression algorithm of choice. And then to estimate the performance drop of on the target domain, you can calculate the domain shift detection metric because you have the inputs, you don't need the labels for this. And then using this regression line, you will estimate the performance drop, right? So that's cool. However, we know that actually these set of evaluation data sets are non-negligible costs. So we know that you need to make them. But compared to continuously sampling from production and labeling evaluation data sets, this is only done once. And although also they don't have to be from the target domain, they can be from any other domain as long as they're biased. So you can sample them actually with bias from the training domain. And only, as we will show in the next slide, only few of them are required. So we run to evaluate the effectiveness of this method. We run some set of experiments on sentiment classification and post-tagging. We actually calculate a concatenation between Amazon sentiment classification dataset, Yelp, and IMDb for movie reviews. And then we group them into 24 different domains, and this simulates 552 domain shift scenarios. We did the same for post-tagging, so we have the universal dependencies dataset for English, and we can simulate 56 domain shift scenarios. So while doing this linear regression method, we evaluated over mean absolute error, so how much I would predict the performance drop of the model and how actually the model dropped when exposed to evaluation from the target side. And we can find that actually most of the metrics done is doing nicely. The most effective one is actually the PAT star, and it can estimate for you the performance drop of the classifier as low as 2.15% for sentiment analysis and 0.89% for post-tagging. So that's cool, but then still the question, how many evaluation data sets are required to do that? So we do the same experiment by varying the number of evaluation data set. We can find, yeah, there is a correlation, or there is a drop in the error as long as you add more evaluation data set, but using as low as 4 evaluation data sets, you can actually achieve very good performance of the prediction of the performance drop. So to wrap up, we have done some analysis to show that domain shift detection metrics, however, they are very motivated theoretically, they are in practice modeled and task dependent. Therefore, we propose a method to modify them to make them task dependent, and we show that actually in practice they are effective. But also we propose a method to convert these domain shift detection metrics values into actually an actual drop of performance, and we can find that it's cheap and fast and also accurate. Thank you. You can find the paper, and if you don't want to go into the paper, you can read a blog about it, and the code will be available after this talk. Thank you. I'm happy to take questions.
Thanks for the great talk. I have a question. So it seems that you are trying to learn the performance drop on a certain data set distribution, and I'm wondering how far it can generalize over a different data set distribution. So for example, you can imagine that you can push it further to say that the target domain are adversarially perturbed images. Then, do you think you can still generalize in that case?
That's a very good question. I think that's actually what motivated our adversarial domain shift in the first place. So yeah, I think if you skew, so that's why in practice, even then, when we did an ensemble of those, so if we go back to this slide, if we did an ensemble of all those domain shift detection metric, it performed worse, but we can find that actually using a several set of domain shift detection metric is actually nice in practice, because if one of them breaks, the others can hold the prediction drop accurately, right? So we cannot generalize outside of sentiment analysis. We try to collect lots of data sets, but if you scale more than this, it's better to use an ensemble of those metrics. Yeah, thank you.
Hi, thanks for the great talk. I have a question for the evaluation data sets. You mentioned that you did an analysis, essentially how many data sets you need to get a good regression model. And you mentioned you could get these data sets from academia or related tasks. If you wouldn't want to do that, if you basically wanted to annotate your own evaluation data sets, do you have a sense of what makes a good test set for this?
Ask the guys of active learning. But it's a good question, sorry, but yeah, I understand. What can calculate? So I assume you can collecting dataset adversarial way is actually overkill, and it doesn't doesn't inflect the average. So I think in production, if you want to do it in a company in production time, you probably sample of the big events. So if you work in a sentiment analysis company, for example, that works with Twitter datasets, you probably need, you have big events that repeat every 2 years, or World Cup, for example, or Olympics. And you would do it every big event, and you would sample from these. And I think these are, or political campaigns. And you would do it, I think you would do it based on your use case rather than based on some metrics you calculate, right? Because that's what you need. But I think if you want to really break them, you can collect ones that show high variance of those models, for example, of those metrics, right? Something like that, yeah. Thank you.
Well, thanks. That's a great talk and great topic, very practical. So one question I have, you shift distribution 4 times, so generate 4 different data sets, and then you measure what's the performance degradation, right? And then something happens in production, and distribution shifts some other way, like 5th way, and then performance degradation may be very different from the ways that you generated yourself, right? And if you essentially you just hope that it will be similar, but you don't know how it will change in production. And then the problem is that if your model degrades in production, then you wouldn't know. You would just be blind about that if you don't do this labeling and rigorous evaluation, right? True. So did you do any experimentation of how to generate, or how well is your 4 ways generalized to all possible ways of distribution shift in production?
So between that and that is a continuum, right? So domain shifts in different ways, right? But not orthogonal. So what we did is actually, so these are actually 3 different projects that collect 3 different reviews of 3 different lengths. So Amazon's contain reviews of books, which people just say the story, their inflection of that, and how they remember their family when they read this book. But you can find DVDs where they just maybe smaller and shorter, right? But then we add them to Yelp, and Yelp is basically mostly mobile reviews, and they're very short, and they say food was good, full stop. So I think if you think of these as 3 different companies using 3 different reviews, and the domain shift was actually accurate over a combination of all of them, you think, okay, this is in practice very, very useful, right? If you tell me, for example, of it happens, this hypothetical scenario that tomorrow morning this happened, one very positive word like good became so negative, and this is something that's a common thing by the community, for example, so that's very orthogonal to these methods of detection, right? Nobody will be able to detect that. But the good news is that not every day the domain shifts happens in an orthogonal way. It just happens mostly in a repetitive way. So that's why cross-validation, for example, is useful in practice.
Yeah, thanks.
Thanks.
Any more questions? Okay, there's one more.
Hey, thanks for the nice talk. I had a question regarding label shift, because we analyzed the post-tagging task quite thoroughly, and we found out that many things that are interpreted as domain shift are in fact inconsistencies in labeling. And so how can you track this one?
That's a very good question. I gave it some thoughts before. And it's very hard to put a general overview over, because performance drop is general, right? Every label shift or covariate shift makes assumption that the rest of the distribution is fixed. So if you tell me, for example, that you have label shift, then the domain shift, the rest of probability of X given Y is fixed, like the task probability, right? So I haven't given it much of a thought, but I think if you have a label shift, that will affect the confidence at test time, and I think these ones will be affected. Also, if you look at one of the metrics, so one of the metrics we proposed is, sorry, I'll go back, is a reverse classification accuracy family of metrics. And these ones is basically doing some sort of round trip classification. And these basically, if you have a label shift, they will be able to detect it. So the whole idea is to use your classifier trained on your in-domain data set to label pseudo dataset from the target domain. And if your pseudo dataset of, so for example, if you do, I don't know, a sentiment classifier, and at test time you will have all the labels is negative, your classifier, your reverse classifier trained on this pseudo dataset will have another domain label shift, right? So the RCA are actually kind of able to detect label shift.
Okay, let's send the speaker again.